I'd like to introduce TJ Chung. TJ will be presenting RoVista, Measuring and Understanding the Route Origin Validation in RPKI. TJ is an assistant professor at Virginia Tech, coming to us today from Blacksburg, Virginia. This is TJ's first time presenting at NANOG. It's a pleasure to have him here with us. Without further ado, welcome TJ.
Thank you. All right, thanks for the introduction, Phil. Hello, everyone. Thanks for coming. My name is TJ from Virginia Tech. I mainly work on internet security protocols like DNSSEC, TLS, and RPKI, which is today's topic. So previous talk is about RPKI and also ROV. So this talk is about measuring network operators, how they do ROV. So for those of you who are not familiar with BGP, most of you are, I'm pretty sure. So this slide is just to give you a little bit background of BGP. So each network resource owner announces its IP prefix to the rest of the router so that they can learn path toward the origin. So it is like a breadcrumbs. However, it was introduced 1,000 years ago. So at the time, there is no security consideration made. So theoretically, anyone can announce any prefixes, which is called BGP prefix hijacking, and also sub-prefix hijacking, etc. So RPKI is basically a public key framework designed to secure internet routing structures, specifically for BGP. So currently, it is known that more than 50% of IP spaces are verifiable with RPKI. So in a very high level, what RPKI provides is to let the router create a securely cryptographically verifiable database so that it can verify, oh, this announcement is actually come from the legitimate origin. So there are two perspectives in RPKI. The first one is resource owner, such as network operators, needs to create an assertion called Route Origin Authorization objects to claim their resources and to upload it to the corresponding registry. The other perspective is, it is similar to other public key infrastructures protocols. So if the resource owner creates an assertion, cryptographically verifiable assertion, then the other party, client, needs to verify it correctly. So in case of RPKI, routers need to download ROAs and verify BGP announcements against them. So understanding RPKI ecosystem, there are two challenges. The first one is how network operators use RPKI to claim their resources by creating ROA and uploading to their registries, or how network operators use RPKI to filter RPKI-invalid, ROA-invalid prefixes. So actually, understanding the first question is relatively simple. So as I mentioned before, you can just download entire ROA objects from each of the registries and then estimate, oh, this percentage of IP spaces are verifiable with RPKI. However, the other question is really hard to answer because we do not have access to each routers. So because of that, there have been successful previous approaches. The first one is, the most prominent one is BGPsafeyet.com, managed by Cloudflare. So when you go to this website and click that test your ISP button, internally what it does is, it tries to look up two contents. One is from the IP address of which IP prefix is actually RPKI valid, and the other one is from the invalid. So if your computer can successfully fetch two contents, it means RPKI invalid prefixes were not being filtered. So your ISP and all the ASes along the path between you and this server, they do not do ROV. Or network operators do some collaborative work together. So there is a spreadsheet called RPKI exposed. It is a cross-source-based spreadsheet managed by network operators so that they can specify their ROV policies here. Or we can rely on official blog posts, Twitter, mailing list, and etc. So as you can tell from these previous approaches, sometimes network operators change their ROV policies. So in that case, this spreadsheet information or this blog post can be stale. So to solve this challenge, our research team has developed a tool called RoVista. So RoVista relies on two main ideas. The first one is the graph shows the RPKI valid variable prefixes, and the x-axis is the date. So as you can tell, nowadays 50% of IP spaces are verifiable with RPKI. However, regardless, there are still about 0.5% of RPKI covered BGP prefixes, announcements, are actually RPKI-invalid. It is because maybe attackers or some misconfigurations. So our idea is, what if we can measure whether an AS cannot reach only to these RPKI prefixes? Then it might indicate that the AS might do some ROV. Then the next question is, how can it measure the two remote end host connectivity? So we are using IP-ID side channel techniques, which allows to infer the connectivity between two remote end hosts. So I'm going to show you how this technique works. So before that, let me first introduce some preliminaries. The first one is TCP Handshape. I'm sure that you guys all know about this, but let me just recap it. So sender can send a SYN packet so that the receiver reply back to SYN plus ACK packet, and then finally reply back to the ACK packet so that we can create a TCP channel. If the receiver, even if the receiver sent a SYN plus ACK packet, but for some reason sender does not respond to, then receiver may wait a couple of seconds, 2 or 3 seconds, and then it triggers retransmission timeout, and receiver sends another packet. Or receiver sends a SYN plus ACK packet to the sender even though the sender never initiated the communication. Then sender may complain that, hey, I never initiate this conversation. Please reset it. Another preliminary is IP-ID. IP-ID is first introduced by RFC 791, originally designed to assist the packet fragmentation reassembly by assigning a unique identifier for each packet. So there are multiple schemes to assign IP-ID for each packet. Sometimes it can be random, or the oldest methodology is global counter, which is increments the IP-ID value by 1 whenever it sends a new packet, regardless of the destination IP address. So now I'm going to merge these two different techniques in together to tell whether we can measure the connectivity between two remote end hosts. So here, we are the observer. And also, I want to know if B can send a packet to A, or A can send a packet to B. So the basic idea is really simple. So measurement client is right there. And also, we're going to call the reflector for the host using global IP-ID counter, which means whenever this host sends a packet, it increments the IP-ID value by 1. So we're going to keep measuring the IP-ID values by sending a SYN packet to the reflector. And if the reflector sends back to us with the SYN plus ACK packet, then we can record this IP-ID value. So for example, let's say this is 1. And then we're going to send a spoofed SYN packet to a target to make it send a SYN plus ACK packet to a reflector. Then, as I showed you earlier, the reflector has never initiated the communication before, So reflector will complain that, hey, I never initiate these conversations by sending reset packet. If we measure IP-ID value of the reflector again, then we can confirm that, oh, it is incremented by 2 because the reflector just sent a packet to a target. So if we measure again, it will be just 4. So there can be 3 cases. The first one is whether there is no filtering happening at all between the reflector and the target. Or there can be inbound filtering from the perspective of the reflector. Or there can be outbound filtering from the perspective of the reflector. So our goal is to disambiguate these 3 cases. So now, our measurement client will keep sending a SYN packet to a reflector to keep monitoring its IP-ID value. And then now we are sending 10 spoofed SYN packet, bursty packet, to a target. If there is no filtering at all, then target will send 10x SYN plus ACK packet, which makes the reflector send 10 reset packet, so that we can measure a one giant spike from our measurement client. If there is inbound filtering happening, then because reflector has never received any packet, so we will not send any reset packet at all. So the IP-ID growth pattern will be just flat. In case of outbound filtering, so reflector just sent 10 reset packets so that we can measure one spike, which is very similar to no filtering case. However, target sent a 10x SYN-ACK packet but never responded with the ACK packet, which triggers retransmission timeout, which means target will send additional 10x SYN plus ACK packets to make the reflector resend 10 reset packet. So in this way, by keep monitoring the IP-ID values of the reflector, we can tell the connectivity. So that's the outbound filtering is the case that we are interested in. So now, when we choose a target, we find a host of which IP address is announced through RPKI-invalid prefix. So we call them target. And then, if we find that a reflector cannot send packets to the target, it may indicate that such RPKI-invalid prefixes are filtered by that AS. If we find many reflectors within the same AS, then it is highly likely due to their ROV policy. So by testing with multiple targets, like 20, 25 targets, we calculate ROV score, which is the percentage of filtered RPKI-invalid prefixes on an AS. So if the ROV score is 100%, it means from our measurement perspective, the AS cannot send any packets to that RPKI-invalid prefixes, which means they might deploy ROV. So we have been running this measurement platform since December 2021. We've been measuring around 31,000 ASes over multiple countries. So actually, we are providing all the daily results, updates, and the API source code available on this website. So of course, because we are missing ground truth data set, so we tried our best to manually find the ground truth, which is basically relying on official announcements and the mailing list, not on mailing list as well. So the table left shows the list of ASes doing ROV. So we found that most of them are consistent with our result, but only 3 do not, and which we reach out to them, and only one network operators, BIT, came back to us. And it is because they had enabled the ROV in early 2018, but they retracted because of some bugs in Juniper routers. So let's look at the status quo. So y-axis shows the percentage of ASes with 100% ROV ratio, which is good. And x-axis is from December 2021 and this date. So as you can tell, the graph is growing rapidly, which is good. So this time, 90% of ASes have 100% ROV ratio. However, one thing I would like to stress out that it is 100% ROV score does not necessarily indicate ROV deployment, because if one customer relies on only one upstream provider, and if one upstream provider does ROV, then the customer AS naturally get the benefit, which is called collateral benefit. Right? Now this graph shows the percentage of ASes of ROV score bigger than 0, which means partially protected. And we can tell the percentage of ASes with the such ratio is over 79%. So let's look at 2 case studies. The first one is, then how can RoVista detect ROV impact? So during our measurement period, we find that 2 ASes, Orange and KPN, officially announced their ROV deployment. So the graph shows x-axis is the date, y-axis ROV ratio, ROV scores. So you can tell the ROV scores of these 2 ASes instantly on a given day jumped from 0% to 100%. In case of Orange, they announced their deployment on June 27th, but we detected that actually deployed ROV on June 6th. Similarly, KPN announced in March 16th, but we detected on March 14th. The other one is about collateral benefit. So KPN deployed ROV on March 2022, and their customers, number of customers, also can get some benefit from this ROV policy of KPN. So as you can tell, we measured 6 ASes. 4 of them, we found that their scores also jumped from 0% to 100% on the same date. However, on 2 ASes, they stay same. And using RIPE Atlas Pros, we found that now they can still reach to the invalid prefixes using some alternative routes to another upstream providers. In case of Orange, the scores of all of their customers we measured jumped to 100% simultaneously. So I'd like to talk about the limitation of our methodology. So RoVista is really good for extending the coverage so that we can measure 30K ASes. However, we cannot measure the ROV score of IXPs because it is infeasible for us to find a reflector on IXPs. The second one is we rely on a host announcing RPKI-invalid prefixes using the public BGP collectors like ROVs and RIPE-REs. So we may have a limited coverage. The last one is ROV protection score does not directly indicate ROV deployment. So 100% ROV scores does not necessarily mean that the AS has deployed ROV. So our team is working on another project which is to identify who is actually doing ROV. So here's the quick summary. So RoVista is a data plane, not a contour plane, based methodology to measure ROV status using in the wild RPKI-invalid prefixes. We are poor network researchers. We don't own any IP prefixes. And we are using IPI design channels. So we are releasing our results this URL API. So if you're interested in such as monitoring your customer ASes, how they filter RPKI-invalid prefixes, you can use these APIs. So if you're interested in more details about the techniques and all the details, then you can take a look at our paper. And also, we also still need a ground truth data set. So if you are a network operators and not participating in this survey yet, please help us. Finally, thanks for the all the sponsors we supported so that my graduate students can pay their tuition. Thank you.
Hi, Tony Tauber from Comcast. Thanks for the good work. One other limitation, maybe, I don't know what you think of it, is, it came to mind, is the reliance on being able to send spoof packets, which is, arguably should not
Practicing
be
PCP.
allowed. And yeah.
Yeah.
And, I don't know, traversing how many intermediate places, but in theory, hopefully that capability is lessening, and I don't know if that lessens the or puts at risk the overall methodology.
So we faced a couple of challenges. The first one is, as you just mentioned, we spent many times just to find out the cloud providers that allows us to spoof our service IP address. And also, not to make, because we are making the reflector to send unsolicited traffic. So we are trying to minimize the number of traffic. So we are only sending 10 TCP packet without any payload. So, yeah.
Thanks.
Andrei Robachevsky, Global Cyber Alliance. TJ, thank you for this work and presentation. One question, have you, well, a couple of efforts also trying to measure ROV, APNIC work, and well, yesterday there was a very interesting presentation on another project. Did you try to sort of, cross-check with their data sets just to see what the overlap is?
Yeah, that's actually a really good question. So because I was a Manners mentors as well, so I tried to cross-check with the Manners data set as well. But what we found was 20 or 30% of discrepancy. So yeah, that is the kind of future work. Yeah.
Thank you.
All right, thank you so much.